All right, hello, and welcome back to chapter 2 of our course, Math 3321. I'm Dr. Heath. Today we are going to be talking through section 2.3, which is all about set operations and their properties. So in the last couple lessons, we learned about sets, set equality, one-to-one correspondence, and a little bit about subsets. But now we are going to talk about some other operations and using Venn diagrams to sort and reason with data. So again, these slides are posted on Canvas. I have skipped a few in this presentation just for time's sake and to try to focus on what you really need to know, but those full slides are posted on Canvas. All right, so the first operation we're going to talk through today is set intersection. So if we think about these two sets, C being the set of X, where X is a college graduate, and S being the set X, where X earns at least $40,000, we're probably assuming here that the universal set is just all people. So suppose we want to mail a questionnaire to all individuals in a certain city who are college graduates and who earn at least $40,000. That and tells us that we are looking at the things that are in common to both the sets C and S, which would be the intersection of those two sets. We can visualize this in a Venn diagram where C is represented by this circle on the left, and that's all of the college graduates, and S are all of the people who earn at least $40,000, and that section in the middle is the intersection, the overlap between the two. We can define this and write it with this kind of upside down U. That's our set notation for intersection, and it's denotes all the elements in common to both A and B. So we could write this in set builder notation to say X, such that X is an element of A and X is an element of B. So the keyword again is and, so both of those conditions need to be met. Okay, so we can go through some examples and find the intersection of these sets here. So let's look at A, where A is set 1, 2, 3, and 4. B is 3, 4, 5, and 6. So I'm looking for the elements that are in A and in B. So 1 is only in A, 2 is only in A. However, 3 is in both set A and B, and 4 is in set A and B. 5 and 6, however, are both only in B. So the intersection is 3 and 4. Okay, so what if I think about the set A, where A is 0, 2, 4, 6, etc. B is the elements 1, 3, 5, 7, etc. You might notice A is all of the even natural number or even whole numbers, and B is all of the even or the odd whole numbers. There's actually no overlap here. All of the elements of A, none of them will be in B, none of the elements in B will be in A. So this is actually the intersection will be the empty set. And we could say that A and B are disjoint if their intersection is empty. And then lastly, A is a set of all of the even natural numbers. But B is all the natural numbers, starting with 1, counting up. 2 is going to be in A and B. 4 is in A and B. 6 will be both in A and B. So the intersection of A and B is actually just all of the set A, all of those even numbers. Because 6, 8, all the even numbers will be belong to B also. Okay, so if we go back to that example about people with college degrees and people who earn at least $40,000 a year, we can use a Venn diagram to display some information. So let's say that we are given the fact that 4,800 individuals have college degrees and 5,400 earn at least $40,000. 1,200 have a college degree and make at least $40,000. So I might start with the universal set on the outside. That's just all of the people. And then we have the set of college graduates and the set of people who earn at least $40,000 a year. So when I look at this picture, I know that 4,800 individuals have college degrees. So that's going to be this entire circle here is 4,800. On the other side, there are 5,400 who earn at least $40,000 a year. So the entire set here is 5,400. And the intersection, this section right here, is 1,200. So we might want to ask questions like, how many people have college degrees but earn less than $40,000 a year? Or how many people who earn more than $40,000 a year didn't go to college? And that would be asking questions about these sets that we don't know the numbers for yet. So we could, we could use the information we have here to figure that out. So the easiest way to go about this, in my opinion, is to start in the middle of our Venn diagram and work our way out. So we know that the overlap here is 1,200 because 1,200 have a college degree and make at least $40,000. And then, like I said, I know that the entirety of the set C has 4,800 in it. So this part that's yellow but not purple will be 4,800 minus 1,200, and that's 3,600. And then for the set S, the part that's not in the intersection, I'm going to have 5,400 minus 1,200, or 4,200. So that's typed out here for you. So 3,600 have college degrees but earn less than $40,000 a year. 4,200 earn at least $40,000 a year and don't have college degrees. And here's your textbook's rendition of that. All right, so in the same way, we can think about intersection, we can think about what's called the set union. So the union is where we might want to mail the questionnaire to people who are college graduates or who earn at least $40,000 a year, or both. And then we might want to send our questionnaire to that set of people. And in that case, the union is all of set S and all of set C and all of its intersection. So the union is depicted in this picture here. And we can formally define this using set builder notation and using this kind of funky looking U, long U here to represent union. And it's X such that X is an element of A or X is an element of B, and not explicitly written or both. So remembering that the truth table for our conjunction statement, where we can have or statements saying if P is true or Q is true or both, then P or Q is true. So again, that keyword is or for the union. Okay, so if we look across these same examples and now think about the union, we're just going to be stringing together all of the elements of both A and B. So in the first set, we have 1, 2, 3, 4. In the second set, we have 3, 4, 5, 6. And remembering that we don't repeat elements in a set, we'll have 1, 2, 3, 4, 5, 6 in the union. So all of A and then all of B put together. So again, we have the even whole numbers and the odd whole numbers. So when we union those together, we'll actually get all of the whole numbers, which is just 0, 1, 2, 3, 4, etc. And then lastly, if we union the even numbers with the natural numbers, we're just going to get all of B because every element of A is in B. So all those natural numbers. Okay, so we've talked about set intersection, we've talked about set union, and now I want to talk about set difference. So again, we have these two sets, college graduates, people who earn at least $40,000 a year, The set of individuals earning at least $40,000 a year, but not a college graduate, is the complement of C relative to S, or the set difference of S and C. We write this out by saying B minus A, and that's not usually how we say it because minus is supposed to be relating to numbers and values, not sets. But it's the set difference of A and B is written as X, such that X is in B and X is not in A. So again, we say set difference, not minus. We would depict this here by all of the elements of B, except we take out the elements of A. So the set of elements all in B, but not in A. And this is actually the same thing as if we were to intersect the set B and the set of A complement. So everything not in A. So remembering that the complement of A will be everything that's not in A. So when we intersect that with B, we get that green overlap part. So those two are the same set. All right, so if we take this example, A is D, E, F, B is A, B, C, D, E, F, and C is just A, B, C, we might think about these set differences. So the difference of A and B, if we take the set A and we take away the elements that are in B, we're actually going to be left with nothing because we would remove D, E, and F from A and be left with the empty set. If we think about B and A, the difference going that direction, we would remove D, E, and F from B and be left with A, B, and C. Then if we are going to find the difference between B and C, we would remove A, B, and C from B, and we'd be left with D, E, F. And again, if we take C minus B, we'll be left with the empty set. We have some properties of all of these operations. So intersection and union are both commutative, meaning it doesn't matter the order that we write the operation in. So A intersect B is the same thing as B intersect A, and A union B is the same as B union A. But as we just saw here, the set difference is not commutative. So B minus A is not the same thing as A minus B when we write it with set notation. So in union and intersection, the order doesn't matter because the order of the elements doesn't matter. We also have the associative properties. So across intersection, we can group together the intersection of B and C and then intersect it with A, or we could intersect A and B and then intersect with C. And same goes for our union. The order that we group them in doesn't matter. Again, it's because the order of the elements in the set doesn't matter. Then finally, we have the distributive property of the intersection over union. So if we have A and we want to intersect it with B union C, that's going to be the same thing as A intersect B union A intersect C. We could see this with a Venn diagram. If I want to draw A intersect B union C, so if I say A, B, C, and I want to intersect A, so if I highlight A, with the union of B and C, so the union of B and C is all of this. Then that intersection is the portion covered by both of these things. So this section here. But if I draw it going the other way, if I think about it from the right-hand side's expression, I have A, B, C again. I would take A intersect B. So again, A, B, C. So A intersect B is this section here. A intersect C is this section here. And when we union it together, we again get that same outlined area like we did in the first one. So those two, the distribution of intersection over union works that way. All right, so we can use set notation to describe the shaded portion. So we can either have set notation and make a Venn diagram, or we can look at a Venn diagram and decide how to represent it using the set operations. So all of these examples are going to have several different ways we could think through representing them. So for example, with this example on the left, A, where we have all of A shaded except for its overlap with B, and all of B shaded except for the overlap with A. One way I see us representing this is to say A union B set difference with A intersect B. So that would be taking the union and then subtracting out the overlap. That's one way you could represent it, but there are several other ways to do this. So the first way that our textbook writes it is the way I wrote it, but then you see we also have, if we take the union of A and B and intersect it with the complement of the intersection of A and B, or if we subtract B from A and union that with subtracting A from B, that would also work. If we look at example over here on the right, we have the overlap between A and B and the overlap between B and C. So the first way I see this is A intersect B union B intersect C. Now I know from the distributive property, I could write this differently. I could say that this is B intersect A union C. That's another way. So those are a couple of ways you could write those Venn diagrams. Again, more examples here. I could have the set A difference with B and then take out C here would be one way to do this. They also say that I could have the difference between A and the union of B and C, or to find the difference with A intersect B and then the difference of A intersect C. All right, on the right-hand side, we've got A without B, but including the overlap that it has with C here. So this one's a little tricky, but I kind of see this as two parts where maybe we think about this part of the diagram first. So that would be A union C minus B. And then I would need to include with that, I would need to union the intersection of all three, A intersect B intersect C. So that's one way you could write this. And I think they have that as the first way. Yeah. And then they give us another way we could think about it as well. All right, so again, with Venn diagrams, we can think about what different portions of a Venn diagram mean. So if we have M is the set of all the students taking math and E being the set of all students taking English, then we could describe what this region A, B, and C mean. So A would be all of the math students or students taking math who are not taking English. Region B would be all of the students taking both math and English, so that intersection, excuse me. And then C is going to be all of the students taking English, but not taking math, or the difference between E and M. And then finally, D is the universal set. So all the students who are not taking math or English. So this is the complement of M union E, or the complement of M intersects the complement of E. Okay, so here's an example I really wanted to make sure we got to, because you're going to have several problems like this on your homework. So in this example, you know that there are 110 college freshmen, so that's our universal set of college freshmen. And we know this following information about the number of students who took physics, biology, math, physics and math, biology and math, physics and biology, and all three subjects. So I've got three different sets I'm looking at inside of my universal set. So this is going to be physics, then I've got biology, and I've got math. So let me write that out. So it'll be physics, I'll call that P, biology, and math. So I'm going to be asked questions like, how many students took biology, but neither physics nor math? Or how many took biology, physics or math? How many took none of the three subjects? So my goal is to fill in this Venn diagram using all the information I have. And just like I did in the previous example, the easiest way to do this is going to be to start from the central parts of your Venn diagram, the most overlap, the intersection of all three, and work our way out. So I know that 5 took all three subjects, so I've used that bit of information. 6 took physics and biology. So that tells me that this part here is going to have 6 in it. However, I already have 5 in there who took physics, biology, and math. So there's only going to be 1 that took physics and biology, but not math. Okay. Then 8 took biology and mathematics. So I know going to this section here, we're going to have 8 in that. But I already have 5 accounted for. So 8 minus 5, there are going to be 3 more students in that section. 10 took physics and math. So if I go again to this intersection, 10 need to go there, but I already have 5 accounted for. So 5 more took physics and math, but not biology. All right, so 48 total took math. So I know that this big circle here is going to have 48 in it. I already have 5, 5, and 3, so 13 students counted for in the math section. So if I do a little mental math here, I've got 48 minus 13 is going to be 35. So there are 35 students who took math, but not physics and not biology. 45 total took biology. So if I look at the set I have there, that is going to have 45 total in it. So 1, 5, 3, 9 students are already accounted for. So that means that there are going to be 36 in the biology section that we haven't counted for yet. And then last but not least, we have our physics students. So there are 25 students who took physics. I've already counted 11 of those. So that's going to leave me with 14 more students who took physics, but not math or biology. So if I want to use this information to answer some questions, I can do that. So how many students took biology, but neither physics nor mathematics? That's going to be biology but not physics or math. That's these 36 students here. If I want to know how many took physics, biology, or math, that's going to be the sum of all of these numbers together. So that will be 14 plus 1 plus 5 plus 5 plus 3 plus 36 plus 35. And so I need to add these together. If I try to do this efficiently, I can do, that's 40. These three together give me 20. And then I have 39. So I've got 20 plus 40 is 60 plus 39 is 99. So 99 total took physics, biology, or math. And how many did not take any of the three subjects? So I actually forgot to finish this because I know there were 110 total in the universal set. So that'll be 110 minus 99. 11 students did not take any of the three subjects. So the rest of these slides just show you how to do this without me walking you through it. They create the diagram for you and answer the questions for you. So you can click through these on your own time and be reminded of these without me talking through them. But that is the end of section 2.3 and chapter 2. So now you should be able to complete all of your chapter 2 homework and your chapter 2 supplemental question and discussion board. So I hope that this helps. As always, let me know if you have questions, and I will see you next time.